Ever imagine hitching a ride on, well, a cosmic shortcut? You know, like you see in the movie.
Sounds like the start of a good sci-fi flick.
It does, doesn't it? But that's what we're doing today, taking a deep dive into, well, traversable wormholes.
Those theoretical tunnels through space-time, you mean?
Exactly. The ones that could, at least in theory, make interstellar travel faster than light a reality.
And you know, what's really interesting is we're not just talking about sci-fi fantasies here.
Oh, absolutely not. We've got some actual scientific research to dig into.
Including a fascinating report from the Defense Intelligence Agency.
The DIA. Okay, so when even the DIA is looking into wormholes, you know it's got to be interesting.
Right. So what captivates me about wormholes is that they're not completely outside the realm of possibility, you know?
Right.
Yeah, they're actually rooted in Einstein's general theory of relativity.
Einstein, huh? Always got to be Einstein. But how does that work, like with the whole space-time bending thing?
So picture this. You've got a piece of paper, right? Now fold it in half. Imagine punching a hole straight through.
Okay, got it. Folded paper, hole punch through.
That hole, that's basically your wormhole, a shortcut through the fabric of space-time.
Connecting two distant points in the universe.
Exactly.
Okay, I'm kind of seeing it. But what makes a wormhole traversable? I mean, what's stopping it from just being a cosmic dead end?
Ah, that's the million-dollar question. And that's where things get really wild. Back in 1985,
Back in the 80s, okay.
two physicists from Caltech Morris and Thorne, they published this groundbreaking paper.
Groundbreaking how?
Well, it totally changed how we thought about wormholes. They used Einstein's equations.
Those equations again?
Yeah, to show that these tunnels, they could theoretically be stable enough for travel.
So not just cosmic dead ends anymore, but there's a catch. Right.
Always a catch.
Yeah.
There is one teeny tiny little thing we need. It's called exotic matter.
Exotic matter that sounds, well, a little intimidating, like something out of Star Trek.
It does have a ring to it.
So is this like antimatter, which we've actually observed, or something else entirely?
It's a common mix-up, but no. Exotic matter isn't antimatter. Think of it this way. Everything we see, planets, stars, even us, it's all made of matter with a gravitational pull.
Right, gravity pulls things together.
Exactly. Now, exotic matter, it's theorized to have negative energy density, meaning it would actually repel matter.
It pushes things away instead of pulling them in. That's wild.
That's exotic matter for you. It would have anti-gravity properties, basically.
Okay, I'm starting to see why we need it. But how does that help with, keeping a wormhole open?
Imagine a wormhole just trying to exist,
Yeah.
right? Without exotic matter, it would instantly collapse on itself.
Poof, gone.
Exactly. But with exotic matter, with its repulsive force, we might be able to keep those cosmic tunnels open.
Long enough for something or someone to travel through.
You got it.
Okay, so exotic matter, it's the key to unlocking wormhole travel. But, and this is a big but, does this stuff even exist? Or is it just theoretical equations on a chalkboard?
It's a huge question, and one that's had physicists scratching their heads for decades. And, remember that DIA report we mentioned?
The one that got us started on this whole wormhole adventure.
That's the one. Well, as part of their Advanced Aerospace Weapons System Applications program, they looked into this.
The DIA researching wormholes. Okay, now that's really mind-blowing. They must have some pretty wild ideas about how to use this technology.
Well, we can only speculate on that, but their report definitely takes exotic matter very seriously.
Seriously, how so?
They acknowledge that it's strange, even by physics standards. The report actually says exotic matter violates the energy conditions.
Waning.
Meaning it breaks some fundamental rules of classical physics.
Okay, we're talking about some really weird stuff here. But they didn't just say, hey, this breaks the rules, let's move on, did they? Did they actually try to figure out how to generate this exotic matter?
They did. And it's where things get really interesting. The DIA highlighted a couple of potential methods, both rooted in some pretty complex physics.
Hit us with it. We're not afraid of a little complexity.
All right, here we go. The first one involves something called squeezed quantum vacuum states.
Squeeze what now? Okay, you're losing me a little bit.
Okay, bear with me. It's a bit of a brain twister. We're talking about manipulating the quantum vacuum, which, believe it or not, isn't actually empty.
It's not.
Nope. It's actually buzzing with energy fields that are constantly fluctuating.
Okay, that's already pretty wild. What does squeezing have to do with it?
Imagine squeezing a balloon. You're decreasing the uncertainty in one direction, but increasing it in another, right?
Yeah, it makes sense.
Well, similarly, by squeezing the quantum vacuum, we might be able to create regions of negative energy density.
And that's what we need for our exotic matter,
You
right?
got it.
So we're talking about what? Squeezing the fabric of reality itself. Has anyone actually managed to do this, or is it all theoretical?
Believe it or not, there have been experiments. One used a continuous wave diode laser and some atomic rubidium vapor.
A laser and vapor.
They actually generated what's called squeezed light, a real demonstration of a squeezed vacuum state.
So it's not just theory. We've actually created these squeezed states in a lab?
That's amazing. So are we saying we're on the verge of creating wormholes?
Hold your horses. While it's promising, there are some big buts. Remember, these experiments, they're dealing with incredibly tiny scales. We're talking about the subatomic world here. Creating enough exotic matter for a wormhole, that would be like comparing a drop of water to the entire ocean.
Okay, so we've got a long way to go. What about that second method the DIA talked about? The other way to create exotic matter, right? That one's a little different. They call it gravitationally squeezed vacuum electromagnetic zero-point fluctuations. Essentially, it revolves around the idea that really strong gravitational fields, like those around planets and stars.
Big stuff.
Exactly. Well, those fields could potentially squeeze the quantum vacuum naturally.
So instead of lasers and vapor, we're talking about harnessing the power of gravity itself. Talk about aiming high, but would it actually work?
It's something predicted by theory, but the effect is expected to be super small.
Yeah.
Especially around something like Earth. However, if you go near a black hole...
A black hole?
Yeah, near a black hole, the effect, it might actually be big enough to be measurable.
Wow. So we might find evidence of negative energy near a black hole. That's both amazing and terrifying at the same time.
It is. It's like searching for the universe's most powerful batteries in the most extreme environments you can think of.
Definitely not a place I'd want to be. But hey, I'm all for pushing the boundaries of science, even if it means getting a little close to a black hole.
Me too. But before we go chasing after black holes, let's clear up something from the DIA report. They use the term Stargates, which might be confusing for some people.
I'll admit I was a little confused too. Stargates, wormholes, are they the same thing? Or is there a difference?
So a Stargate, it's kind of like a specialized type of wormhole. Imagine the classic wormhole with its spherical throat, right?
Or the paper example.
Exactly. Now, a Stargate, it has a flat face shape for its throat.
Okay, so instead of a sphere, it's more like a flat circular opening. Does that change how it works?
It does. A traveler going through a Stargate's throat would just smoothly move into another space-time region.
Smoothly. No crazy gravitational forces trying to rip you apart. That's a pretty big difference.
Right. No crushing gravity, which would be a major plus for any interstellar travelers out there.
I bet. But how does a flat-faced wormhole, a Stargate, how does it even form? Is it the same process as the spherical ones?
Well, the DIA talks about something called a thin shell formalism to work out the properties of a Stargate.
Okay, you're going to need to break that down for me.
Okay, imagine you've got two flat regions of space-time.
Let's call them, what, space-time sheets?
Sure, space-time sheets. So you take these two sheets and you remove identical sections from each.
Okay, like cutting out the same shape from two pieces of fabric?
Exactly. And then you connect the edges of those cutouts with this, well, a thin shell of mass energy.
It's like cosmic sewing.
Sort of. It's manipulated the very fabric of space-time.
That's mind-blowing. But can we actually do any of this in reality, or are we just talking about theoretical possibilities?
No, that is the million-dollar question, isn't it? And it's one we're going to keep exploring as we go further down this wormhole, rabbit hole, while we're trying to wrap our heads around the science of all this.
Which, believe me, is a lot to take in.
It might be helpful to actually visualize what a wormhole might look like.
Now, that's a question that sparks the imagination. So if we could actually see one of these things, what would we see? A swirling vortex? A shimmering portal? What's your take?
Well, let's start with the classic wormhole, the Morris thorn type with a spherical throat.
Okay, the spherical one.
That kind of wormhole, it would act like a topological inversion, if you can believe it.
Okay, you're going to have to translate that for me. Topological what now?
Essentially, instead of looking straight through the wormhole to the other side.
Right, like a window into another part of the universe.
Not exactly. You'd actually see a distorted mirror image of whatever distant region of space it's connected to.
Wait, a distorted mirror image. Okay, now I'm really having trouble picturing it. Can you give me a real-world example?
Think about those Christmas ornaments, the shiny reflective ones.
The ones you see your reflection in, but all warped and weird?
Precisely. Imagine that, but instead of reflecting a room, It's reflecting a whole other part of the universe. That's what the wormhole's gravity would do to the light passing through it.
Okay, that's a seriously trippy visual. So with the spherical wormhole, you wouldn't actually see it a clear path through. You'd see a distorted reflection of the other side all squeezed into this spherical shape. What about Stargates, those flat-faced ones? Would those look any different?
Stargates, oh, those are a different story. With their flat-faced design, they wouldn't distort the image the same way.
So you'd actually see through them?
Potentially, yes. They'd behave more like windows, giving you a clearer view of whatever lies on the other side.
A window to another part of the universe, maybe even another universe entirely. It's really incredible to think about these cosmic shortcuts potentially existing out there, which begs the question, could there be naturally occurring wormholes out there, ones that were formed without us needing to build them?
That's a question that's kept physicists and astronomers guessing for years. And to be honest, we don't have a definitive answer.
But if they could exist, how would we even begin to look for them? What kind of signs should we be looking for?
Well, one of the most promising methods relies on gravitational lensing.
Gravitational lensing. Okay, remind me what that is again.
Remember how we were talking about a wormhole warping the path of light?
Right, like that distorted mirror effect.
Exactly. Well, if a wormhole happens to lie between us and a distant star or galaxy, its gravity would bend and distort the light coming from that object.
Creating a kind of cosmic magnifying glass?
In a way, yes.
Mm-hmm.
And these distortions, they'd create very specific patterns. So by looking for these unusual patterns of distorted light, we might be able to infer the presence of a wormhole.
So we wouldn't be looking for the wormhole itself, but rather its fingerprint on the light passing by it.
You got it.
Yeah.
It wouldn't be easy, though. It'd be like searching for a needle in a cosmic haystack.
And I imagine we'd need some seriously powerful telescopes to even have a chance of spotting these distortions. Are there any other telltale signs we could look for, aside from these lensing effects?
There are a few other more speculative ideas out there. For example, some scientists have proposed looking for unusual radiation patterns. The thought is that these patterns may be caused by the interaction of exotic matter with normal matter near the wormhole.
So not just distorted light, but weird energy emissions as well. Okay, now we're talking about some seriously high-tech detective work.
You could say that. But again, detecting these emissions would be incredibly difficult, even with our most advanced instruments.
It's like the universe is playing hide and seek with some of its most fascinating secrets. But that's what makes it so exciting to explore. So we've talked about naturally occurring wormholes, but what about the prospect of actually building one? That seems like a whole different challenge, wouldn't you say?
Oh, absolutely. Creating a wormhole isn't just some weekend project. And to be honest, even the DIA, in their report, acknowledges the massive hurdles involved in building a traversable wormhole, even a small one.
So no shortcuts when it comes to shortcuts through space-time.
Not exactly. But they do highlight some major challenges, starting with one we've already touched on: negative energy.
The key ingredient in our exotic matter recipe.
Right. But here's the thing. A wormhole with a throat just 1 meter in diameter, something you could barely fit through.
Not exactly spacious for interstellar travel.
Not at all. But even that tiny wormhole, it would need a mind-boggling amount of negative energy to stay open.
How mind-boggling are we talking?
The equivalent of the mass of Jupiter. That's how much negative energy we need for a 1 meter wormhole.
The mass of Jupiter. Okay, I think we could all agree that's a lot. But let's say, just for argument's sake, that we could somehow generate that much negative energy. Then what? How do we even begin to control it? It's not like we can just mold exotic matter like clay, right?
You raise a great point. And the DIA report addresses that too. They emphasize the sheer precision needed to manipulate spacetime. We're talking about manipulating the very fabric of reality with incredible accuracy.
And I'm guessing one wrong move could have some pretty disastrous consequences.
Absolutely. One miscalculation, and we could end up with a spacetime catastrophe on our hands. It wouldn't be pretty.
Okay, so we've got the negative energy problem, which is already huge, but then there's the whole issue of actually engineering a stable wormhole. What other engineering challenges does the DIA report highlight?
Well, there's the stability problem we just mentioned. Keeping a wormhole open long enough for something to travel through it, it's no easy feat. We need to constantly counteract its natural tendency to collapse in on itself.
Like trying to hold a soap bubble open with a high-powered fan?
A pretty apt analogy. And then there's the whole issue of navigation. Even if we could create a wormhole and keep it stable, how do we make sure it goes where we want it to go? Space-time is a pretty complex thing to navigate, especially when you're bending and warping it to your will.
So we've got the energy problem, the stability problem, and the navigation problem. Interstellar travel via a wormhole is starting to sound a lot more complicated than just stepping through a cosmic doorway.
You're telling me. But what's amazing about the DIA report is that it doesn't just present a laundry list of impossible problems. They actually offer some potential solutions. And some of them, let me tell you, are pretty out there. One area that seems to have caught their attention is something called emergent space-time gravity theories.
Emergent space-time. Okay, that one definitely goes over my head. What's that all about?
Well, it's a pretty radical idea, even for theoretical physics.
How so?
It suggests that our current understanding of gravity, the one based on Einstein's general relativity,
Which, as I understand it, is kind of a big deal in the world of physics.
it's the foundation of how we understand the universe on a large scale.
Right. Planets, stars, black holes, all that good stuff.
Exactly. But these emergent gravity theories, they suggest that our understanding might be, well, incomplete.
Incomplete. You mean there's more to gravity than even Einstein realized?
Potentially, yes. These theories propose that gravity, instead of being a fundamental force,
Like one of the 4 fundamental forces of nature we learned about in school.
exactly, they suggest it might actually emerge from something even more fundamental.
Something more fundamental than the fundamental forces. Okay, now you're really blowing my mind.
A pretty wild concept, I know. It's like this. Think about temperature.
Temperature. What does that have to do with gravity?
Well, temperature, it's not really a thing in itself.
Right.
It's a way we experience the collective motion of tons of tiny molecules.
Okay, I see where you're going with this. So you're saying gravity might be similar.
Exactly. Emergent gravity theories suggest that gravity could arise from the interactions of countless microscopic entities or events at the quantum level. It's like, imagine a giant wave in the ocean.
I can picture that.
That wave, it seems like one massive thing, right? But it's actually made up of billions of individual water molecules all moving together.
Okay, that makes sense. So instead of gravity being a top-down force, it could be this bottom-up phenomenon bubbling up from the quantum realm.
Exactly. And if that's true, if we can figure out how to manipulate those underlying processes,
We might be able to manipulate gravity itself.
you got it. And that could change everything, not just for wormhole travel, but for all sorts of technologies we can't even imagine.
It's like the difference between trying to move a mountain with your bare hands and figuring out how to control the tectonic plates beneath it.
It really is. And while it's still very early days for these theories, even the possibility that they might be true is incredibly exciting.
It definitely makes you think twice about what we still don't know about the universe. But let's bring this back down to Earth for a second, or at least to the realm of what we can do with our current technology. Even if we assume exotic matter is the key to all of this, how do we even begin to study something so elusive in a lab?
Yeah, that's the million-dollar question, isn't it? We can't just, order a wormhole-sized chunk of exotic matter from Amazon.
I checked it's not on Prime delivery. But seriously, where do we even begin?
Well, the DIA report, it does offer some clues. It suggests that even minuscule amounts of negative energy,
Like really, really tiny amounts.
exactly, even those should have detectable effects on their surroundings.
So even a little bit of negative energy should create some kind of measurable change. It's like trying to find a single snowflake in a blizzard.
In a way, yes. But just like a snowflake has a unique structure that sets it apart from every other snowflake, negative energy, it should have its own unique signature.
So how do we go about finding that signature? What are we looking for?
Well, remember those unique lensing and chromaticity effects that we discussed earlier? Those could be our clues.
So even the tiniest bit of negative energy should distort light and color in a way that we can detect.
Potentially, yes. The trick is building instruments sensitive enough to pick up those subtle changes.
I can imagine that's no easy feat. What kind of instruments are we talking about?
One really promising area involves using ultra-high-speed optics and something called optical cavities.
Optical cavities. Okay, you're going to have to explain that one.
Imagine a tiny chamber built with incredibly precise mirrors on the inside.
Okay, like a tiny hall of mirrors.
Sort of. The idea is that we can trap light inside these cavities, and by carefully analyzing how the light behaves.
But we could detect any tiny changes caused by negative energy.
Exactly. Think of it like this. You've got a perfectly tuned guitar string, and you're listening very, very carefully. If something, even something incredibly light, brushes against that string, you're going to hear a change in the tone, right?
Yeah, even a tiny change in vibration would be noticeable.
Precisely. It's the same concept with these optical cavities. We're creating an environment where even the slightest interaction with negative energy should create a detectable change in the trapped light.
It's mind-boggling to think that we're manipulating light at such a precise level, all in pursuit of understanding something as exotic and elusive as negative energy.
It really speaks to the dedication and creativity of scientists who are pushing the boundaries of what we thought was possible.
Absolutely. And it's a good reminder that we're really just scratching the surface of what there is to know about the universe.
Well, this has been an amazing deep dive, to say the least. We've gone from imagining ourselves hitching rides on cosmic shortcuts to talking about manipulating the very fabric of space-time. It's been an incredible journey. It really has.
Yeah.
And you know, what I find most fascinating is how even the most outlandish ideas, like wormholes, can lead to incredible scientific discoveries.
Exactly. And while we might not be punching holes in space-time anytime soon, the pursuit of these mind-boggling concepts like negative energy and exotic matter, it has the potential to unlock some truly revolutionary technologies.
Technologies that could change our world in ways we could hardly even imagine.
And on that note, we'll leave you with a final thought. The universe is a vast, mysterious place, and we're just beginning to explore its most hidden corners. So keep asking questions, keep looking up at the stars, and never lose that sense of wonder.